Hello, welcome to another stream of caveman coding, programming every day until I land an intern. So today we will be doing the project that we started the last stream, which is making the OS in 1,000 lines. So, oh damn. So yeah, we will try to do. In the last stream, I wasn't able to do much because I had no energies. But this stream, we will be um, you know doing stuff that is important. So let's get on with it. So the last stream we completed the intro, getting started. We were we were on this page and we I think read all of this. No, we read all of this and we were right here. CPU modes. CPU has multiple modes, each with different privileges. In our SCV, SC5, there are three modes: M mode, S mode, U mode, user mode, kernel mode, and mode image. OpenSBI operates. Okay, BIOS. Okay, nice. Um, so this is what privileged instructions. Among CPU instructions, there are types called privileged instructions that applications user mode cannot execute. In this book, we use the following privileged instructions. So these are the privileged instructions that the user mode cannot use. Only the kernel can use. I think so. CSSR, RD, SCSR is basically read from CSR. Okay, CSR CSRW CSR comma RS is write to a CSR. So RS will be assigned to CSR. Read is basically read into RD from CSR. Okay, CSSRW read from and write to CSR at once. So read from CSR, which is RD, is equal to um, CSR. Also, when you do basically CSR is equal to temp. Okay, and then you're assigning RS to CSR, and then you're reading from temp to RD. Cool. So you're assigning RS to CSR, which is to write into CSR. Okay. S return is basically return from trap handler, restoring program counter operation mode. Okay, restoring program counter operation mode. Return from trap handler. Okay, that is interesting. What is trap handler? We'll find out. But trap handler is the code that will run. As far as your trap is something, let's see, is the code that will run when trap is triggered. In example, the OS will have an install handler. Trap instruction jumps to kernel mode. Then trap handler jumps to desired handler. And the execute fork is finished. The OS calls return from trap instruction makes the program go back to user mode. What exactly is a trap handler? Also, if you may, what is a trap table? Trap handler is the code that will run when the trap is triggered. Okay. In example, OS will have installed a handler, told the CPU a memory address code to run when the trap happens, and the handler will execute the system call. It is not the program that jumps to kernel mode. The program is interrupted immediately after it triggers the trap. Okay, it is not the program that jumps to kernel mode. The program is interrupted immediately after it triggers the trap. Execution resumes with the trap handler. Okay. This way, the GDS program that runs in protective mode, operating system runs in privileged mode, CPU hardware that enforces that currently executing code cannot break out of protected mode and can hand off control between each other. Also know that modern CPU have dedicated instructions for system calls, a mechanism that is more efficient than trapping but conceptually works the same, and there are other traps and interrupts used for different purposes as well. They provide the basic mechanism for stopping sequential program execution and do something else in reaction to some kind of event. What is this? Okay. IDT to depend how to transfer control when a trap occurs. The x86 allows up to 256 different interrupt or execution entry points into the kernel, each with a different input interrupt vector. A vector is a number between 0 and 256. Um, so a trap is essentially um, when there's something that goes wrong, is it? Something happens when special events occur. Okay, in case system call, program executes trap instruction jumps to kernel mode. Then trap handler jumps to desired handler. He says that the OS will have installed a handler and the handler will execute the system call. It is now the program jumps to kernel mode. Okay. So the handler jumps into the um, handler will execute the system call and it's not the program jumps into the program interrupt immediately after it triggers the trap. Execution resumes with the trap handler. Alright. Svens.vma clear transition look aside buffer. Okay, all of these things that we read in COA, which is computer organization architecture, all of these things are, you know, here. CSR, control and status register. So what is CSR? It is control and status register. Is a register that stores CPU settings. The list of CSRs can be found specification. So control and status register. Okay. Okay. Hmm. Hold on. Okay. So the RASC 5 ISIS specification extensions and supporting documents that could have developed ratified. Okay. Um, all of these things. Let's see what this guy, is in store for us. This is a source CPU settings. That's what he told. That's what this website says. Okay. Tip some instructions like sthread do some somewhat complex operations. Return from trap handler. Okay. To understand what actually happens, reading emulated source code might be helpful. Particularly RVEMU is written in an intuitive and easy to understand way. Asset implementation. So this is a tip, and I don't think there's specifications here. Where are the specifications? So this is what it is. The asset, is that asset implementation? Okay, I barely understand what is going on in this. This is which, what is this even what is the language for this? This .rs. What does .rs mean though? What does .rs mean, bruh? I never seen this in my entire life. This definitely looks intimidating, man. Okay, inline assembly. Do you have specifications here? All of these useless links, man. What do I even click on? efficient trace ISA profiles, community source repository, ISA sources for repository, ISA manual. Okay. Repo activity. Mm-hmm. Doc resources, src dependencies, dot github and stuff. Dude, what is this? I do not understand anything, man. Inline assembly. In following chapter, you will encounter special C language syntax like this uint32 underscore t value. Okay, that is this I understand. And what is this? ASM volatile CSR R percentage zero spec is equal to uh, R value. This is inline assembly, a syntax for embedding assembly into C code. While you can write assembly in separate file, dot as extension using inline assembly is generally preferred because what is inline syntax for embedding assembly into C code. Okay. While you can write assembly in a separate dot as extension using inline assembly is generally preferred because you can use C variables within the assembly. Okay. Also, you can assign the results of assembly to C variables. Okay. Okay, nice. So this is does ASM mean assembly? Probably. And there's underscore volatile underscore CSRR percentage zero spec R value. So I think your CSR is just the CSSR is basically the CPU status, right? Status control and state register, and the spec is, so you're setting CSSR to 0 and spec to R from value. I do not understand it, but okay. You can leave register allocation to the C compiler. That is, you don't have to manually write the preservation and restoration register to be modified in the assembly. Okay, cool. How to write inline assembly? Inline assembly is written in the format ASM volatile assembly. Output operands, input operands, clobbered registers. Okay, nice. Interesting. Volatile, so ASM volatile assembly. So there's this string, and then you do output operands, input operands, clobbered registers. Indicates it's an inline assembly. Volatile tells the compiler not to optimize the assembly code. Okay, not to optimize the assembly code. Okay. Assembly code written as a string literal. Okay. C variables store the results of the assembly. C expressions to be used in the assembly. Global registers are registers whose contents are destroyed in the assembly. If forgotten, the C compiler won't preserve the contents of the register and will cause a bug. So, whose contents are destroyed in the assembly? Okay. If forgotten, the C compiler won't preserve the contents of the register and would cause a bug. Output and input operands. Output and input operands are comma separated. Okay. And each operator is written in the form constraint C expression. The format constraint C expression. Constraints are used to specify the type of operand and usually is equal to R register for output operands and R for input operands. As written in the format constraint C expression, constraints are used to specify the type of operand and usually is equal to R is register. Okay, so that's why we used is equal to R, this is the register. Okay, for output operands and R for input operands. So this is the output operand, input operands, and output operands. Damn it, output operands and input operands. So this is actually the input operands. Okay. Okay, this is the string literal, I guess, and this first thing is input operand and is equal to R is used for output operands. Not quite getting it. as of now, but okay. Output and input operands can be accessed in the assembly using percentage 0, percent 1, etc. in order starting from the output operands. Okay, let's see the examples. So you're defining the value here, ASM volatile CSSR percentage 0 spec. Okay, what is this? This reads the value of spec. Sorry, SCPC. What is SCPC? SCPC CSR using. Okay. Oh, okay. You're basically naming the CSR variable called SCPC and then using the CSR instruction. Oh, assigns it to the value variable. Okay, value of this thing, and you're assigning it to the value variables. Percentage 0 corresponds to the value variable. Oh, okay. So the output input. So this is the output. I'm sorry. This is the operands. So using the CSSR instruction, CSSR, which means that you're reading into CSSR. Um, that's what it is, right? You're reading into CSSR. Oh, I'm sorry. Read from CSSR. Read from CSR and write to CSR. Okay. Okay. What is reading into CSSR anyway? Okay. You're reading from CSSR. So you're reading from CSSR and assigning it to value using this thing, which is output operand, and percentage correspond to the value operand. Okay, value variable. Interesting, pretty cool. Okay, now let's see the other example. Scratch percent 0. Um, this I think dark mode is only better to do. Okay, this is much better. That's much better. Let's train it on the ice. Okay. CSRW scratch. Dispatch 123 to the scratch CSR. So scratch, okay, using the CSRW instruction. Our constraint is the input containing 123, and it would actually look like. So this actually this is the inline assembly in the C code, and this will actually look like this in the actual assembly code, which is li A0123. You're setting 123 to A0 register, okay, and then you're doing CSRW, write the value of A0 register to scratch register. Although okay, nice. Although only the CSRW instruction is written in inline assembly, the li instruction is automatically inserted by the compiler to satisfy the R constraint value in register. It's super convenient. Nice. Inline assembly is compiler specific extension not included in the C language specification. You can check detailed usage in GC's documents. However, it takes time to understand because constraint syntax differs depending on CPU architecture and has many complex functionalities. For windows, I recommend to search for real world examples. For instance, here are some access where good references. So it's part of GCC and microkernel book. Dude, what is this, man? This is what is this? Microkernel book. This is Hinawas. Okay. Um well, actually starting inline. Nice. So this is the assembly code, if you may. Okay. Volatile, that's where they're using head here. So let's try to decode this. This is the assembly. ASM is the inline assembly. Volatile is telling the compiler to not destroy it. I guess to not, what is it? To not optimize it. Okay. To not optimize it. LH. What is LH command? But we do not know the LH command. But okay. 0 1. This is the input. This is the output. You're writing into the output from the input. Percentage 0, percentage 1. Okay. Oh, okay. Nice, nice, nice. Nice. I got it. 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 So this thing is basically this is the assembly code in this is the assembly string. That's what he told. I'm dumb. I did not understand it then, but okay. So this is the assembly code, and you're doing the input and output. Because it's reading only, you're doing just the output from the CSR basically. From the SCPC, you're reading into value, nice. And then RW is from basically you're reading this the input, output, and clawbird. Is that clawbird? Yep, clawbird is okay, but anyway. So you're reading from this to, and you're writing into this, right? Yeah. Okay. Well. Okay. 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 Now you're doing overview. Let's do overview. Before starting the building notes, let's quickly get an overview of the features we will implement. Features in 1K LOC OS. Okay. In this book, we'll implement the following major features: multitasking, switch between process to allow multiple applications to share the CPU. Okay. Exception handler, handle events requiring OS intervention such as illegal instructions. Um. Okay. Okay. Handle events requiring OS intervention such as illegal instructions. Wow. Paging, provide an isolated memory address space for each application. Nice. System calls allow applications to call kernel features. Device drivers abstract hardware functionalities such as disk reader write. Okay. 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 Nice. File system manage files on disk. Okay. Command line shell user interface for humans. Wow. I think that's a very good, you know 1K lines of code for building an operating system. That's actually brilliant. If we're gonna do all of this, that's crazy. Let's try to do it. I'm excited. Features not implemented. For any major features not implemented in this book, interrupt handling. Instead, we'll use a polling method. Periodically check for new data on devices, also known as busy waiting. Okay. Right. Okay. So it's not non-blocking, is it? Right. His Okay, yeah. It is blocking and not non-blocking. Okay. Timer processing, preemptive multitasking is not implemented. Oh, okay. We'll use cooperative multitasking where each process voluntarily yields the CPU. Okay, nice. Preemption is not implemented basically. Okay. Right. Inter-process communication features such as pipe, Unix, domain, socket, and share memory are not implemented. Interesting. Interesting. The sockets are not implemented. Okay. Multi-processor support, only single processor supported. Nice. I mean, that's good enough for me, I think. It's only at the beginning, so it's good. We'll be scats included and the final file structure will look like this: disk common.c, common.h, kernel.c, kernel.h, kernel.ld, shell.c, user.c, user.h, user.ld, run.sh. So disk is the file system contents. Okay, so common.c is the common library, printf, memset. Common.h is definition, structs, and constant. So the common library, nice. Structs and constants, nice. um, Kernel, process management, system calls, device drivers, file system, definition, struct, and constants. Okay. Linker script, memory layout definition, command line shell, shell.c, user.c, user library, functions for system calls, user library, definition, struct, and constants. Okay. Linker script, build script. In this book, user learn is sometimes abbreviated as user. Considers applications and do not confuse it with user account. Okay, cool. Pretty cool, man. Let's move on. Boot in the kernel. So we are going into the meat of it, right? When a computer is turned on, the CPU and stuff and starts executing the OS. OS enters the hardware and starts the application. The process called booting. Nice. Okay, so the booting is basically starting the applications and initializing hardware and starting the application. What happens before the OS starts in PCs? BIOS, BIOS or UAFI in modern PCs initializes the hardware, displays the splash screen, and also OS from the disk. In QEMU virtual machine, OpenSPI is equivalent of BIOS and UEFI. Okay, nice. Okay, supervisor binary interface. Mm, is an API for OS kernels but defines what the firmware Open SPI provides in OS. Okay, it's an API for OS kernels. The SPI specification is published on GitHub. All these random links that I have, but it's too much, man. So this is what these the SPI, which is the supervisor binary interface, which is just an API for OS kernels. Okay, it defines features such as displaying characters on the debug console, serial port, reboot or shutdown, and timer settings. Okay. Displaying characters on the debug console, serial port, reboot or shutdown, timer settings. A famous SPI implementation is OpenSPI. Starts by default, performs hardware specific initialization and boosts the kernel. Basically, it's just basically the initialization of the hardware and then booting the kernel is what SBI does, right? So it's an API for all kernels. Okay, just the binary interface and supervisor binary interface, which supervises the booting of the OS. I think that's a correct way to put it. I guess it defines useful features such as displaying characters on debug console, serial port, reboot or shutdown, and timer settings. Okay, let's boot OpenSPI first. Let's see how OpenSPI starts. Create a shell script named run.s such as follows. Let's just try to do this. Let's just create a disk and then uh, work from there. So yeah, okay. What are we doing? We're doing make directory. What is it? Disk, right? Okay, we're in disk. So we are in disk right now. Okay. Now, what do we do? We are creating a run.sh shell script, and we're plus x. We're doing plus x run.sh. I think plus x. What does chmod command do? Plus x is actually just execution, right? So you're giving execution commands to run.sh, is it? Is that is that good? Is that a good explanation? So execute permission for files, search permission for directories. Oh, nice, nice. Okay, nice, cool. So let's do that. Chmod plus s x run.sh. Okay, okay. So we are giving an execution permission to the file named run.sh. Cool. And then we're going to run.sh and we're writing this. QEMU takes various options to start the virtual machine. What is QEMU? Uh, is a free and open source emulator that uses dynamic binary translation to emulate a computer's process. Okay, to emulate a computer's process, that is, to translate the emulated binary code to an equivalent binary format which is executed by the machine. Oh, okay. Mm, not really, helpful, but okay. Let's try and explore QEMU later, but okay. So QEMU file path takes various options. Start the virtual machine. Error options using the script. Machine VAT. Start a VAT machine. You can check other supported machines with the machine. Okay. Use the default firmware. OpenSBI in this case. No graphics. Start QEMU with a GUI window. Connect QEMU standard input output to the virtual machine's serial port. Specifying man allows switching to the QEMU monitor by pressing Ctrl plus A then C. Solve the emulator without rebooting, useful for debugging. No reboot is basically if the virtual machine crashes. Stop the emulator without rebooting. You can check the path to homebrew QEMU with the following command. Okay, let's do that. ls brew prefix bin QEMU system RSA 32. Okay, we have it here. I think we installed it yesterday, that the commands that we ran yesterday. So QEMU system RSV. Let's see what's in this contents. I don't think we can do that, but cool. Cool. So okay. Mm-hmm. So I think this is just the set xeqe qme file path system. Okay, so that's the okay, there's a name. Okay, okay, cool. The path you're specifying, and then what is this? In shell. Powerful tool that is used for controlling the behavior of the shell and environment image. In shell scripting is powerful tool that is used for controlling the behavior of the shell and environment image description. Mm-hmm. Okay. So all of these are commands, options. Behave the script and everything execute in the app without any issues. Okay. Okay. Options and arguments. So what are we using here? XQE. So as you, it reads unset variables as an error during substitution. Okay. X as X, where's X? I can't. Okay, here. It prints the commands and their arguments in the same sequence as they got executed. Okay. E use exit when the command exits with a non-zero status. Okay. Nice. Okay. Start QEMU machine word BIOS default no graphics serial mon SRAO no reboot. What is this? So okay. This is the command that we just read. Okay. So this is the machine VAT. Start a virtual machine. You can check other supported machines with the machine. This thing option. BIOS default. Use the default firmware. OpenSBI in this case. No graphic. Start gaming with the GUI window. Without the GUI window. Okay. Serial is connect QM is standard input output of the virtual machine serial port. Okay. Specifying mon allow switching to QEMU memory by pressing Ctrl plus A then C. Oh, okay. Okay. Switching between the virtual machine and the QEMU monitor. Okay. No reboot if the virtual machine crashes. Stop the emulator without rebooting. Use before debugging. Okay. So let's just try to write it ourselves as much as possible. I don't want to copy anything. So I'm sorry, insert key. I'm still new to okay, still new to Vim. So okay, insert. Okay, so we're an insert, and then what is this thing? Bin. Okay, hashtag this thing slash bin slash bash. Is that even required? I don't know. I think it's just a command. It's just a comment, and then you're doing set XUE. You're doing QE MU file path. Okay, so this is the file path, the comment, and then you're doing QE MU is equal to QEMU system RISV 32. Okay, QEMU system RISV 32. Is that correct? Okay. Start QEMU. Okay, start QEMU. You're doing dollar QEMU because you wanna access the path, right? QEMU. You're doing machine. Is that what? And then you're doing BIOS default. Okay, no graphic. Okay, serial. Okay, serial mon SJO. Okay, right. Okay, then no reboot. Cool. That's cool. And then escape and save it. Right. In macros you can check and then run the script. Okay, let's do that. Okay, not found. So line 4, this is not found. What does this mean? Just try to copy. I know I said I won't copy, but I'm so bad at this, dude. XUE, right? I'm sorry, file path. Okay, so this thing, if I want to select everything, what do I do? I forgot. Do I do how do I select this thing? Select to the end of the file. Let's just check. Select end of the line. Vim. Press all to move to the cursor. How to go to the yeah. Oh yeah. So it's D. So it is D. Oh, I'm sorry. U. Okay. Is D this thing? Oh, nothing happened. Okay. Okay. I want to delete till here. So from this line to the end of the file, end of the line. No, nothing happened. I just did D dollar. Oh, I'm sorry. I'm so bad at this load. I have to type D shift 2. Come on now. I'm just embarrassing myself at this point. Let me get this. Okay, got it. Got it. I'm just gonna copy this. Command C. Command V. Okay, cool. Okay. I'll just do this. It's much better. Okay. Okay, there was some mistake that we did. But okay. Okay, we got it. We got this page at least. Open SPI, platform name and shit, domain name, platform features, hard count, these things. So okay, open SPI displays open SPI version. The version is Okay, it says 15 point something here. 1.5, I'm sorry, 1.5. Platform infusion, number of hearts, CPU cores. Oh, number of hearts of CPU cores. Okay, heart count is 1. Interesting. Okay. It says 16 boot heart PMP count. So 16 cores are there on my system. I'm not sure. Okay. Okay. This because okay, when you press any key, nothing will happen. This because QME's standard input output is connected to the virtual machine's serial port, and the character step is being sent to the open SPI. However, no one reads the input characters connected to the virtual machine serial port, and the character step is being sent to the open SPI. Let's do that. Okay, nothing happens. Okay, cool. Yep. Press controller A. Then CT switch to the QMI debug console, QMI monitor. Okay. This is the open SPI. Okay. You can exit QMI by Q in the monitor. So let's do that to switch to the QEMU debug console. Okay, so in the open SPI, whatever it is, because QEMU started input is connected to the virtual machine serial port. So being sent to the open SPI, no one reads the input characters. To switch to the QEMU debug console, you can exit QEMU by Q in the monitor. Okay. So let's do that. Control A, then C. So we are in QEMU to 9.2 monitor. Okay. Nice. And then queued for quitting. Q. Nice. Control plus A has several features besides switching to QEMU monitor. C key. Okay. For example, pressing the X key will immediately exit QEMU. Okay. C control plus A hatches print this help exit emulator save this data back to file if snapshot toggle console times stamps send break magic SSRQ switch between controller monitors with sense CA. Okay. Linker script. A linker script is a file which defines the memory layout of executable files based on the layout. The disk is a file which defines the memory layout of executable files. I do not understand half of this page, but okay, I'm trying to understand it. So I hope you bear with me. So a linked script is a file which defines the memory layout of executable files. Mm-hmm. So it defines the memory layout. Based on the layout, the linker assigns memory address to functions and variables. Okay. Let's create a new file named kernel.ld. Okay, let's do that. And it says entry of boot sections is equal to this, text is equal to this, row data is line 4, this, whatever this means, whatever this means, whatever this means. Yeah, the key points to the linker script. The entry point in the kernel is the boot function. Oh, nice. The base address is this. The .text object collection is always placed at the beginning. .text .boot. .text .boot section is always placed at the beginning. Okay. Alright. Each section is placed in order of .text .row data .data and .bss. Row data data bss. Okay. So okay. So the base address is this. So basically it basically linker What it does is just the memory layout, basically assigns the memory address functions and variables, and the base address for the function and variables is this, is always placed at the beginning. Each section is placed in order of dot text dot row data dot bss. The kernel stack comes out of the base bss section and its size is 128 KB. This is the kernel stack. Line 4, 128 into 1024, which is the bits basically, so kilobytes. Okay, right, kilobyte 1024 bytes. So you're doing 128 KB of the kernel stack, and stack top is dot. Basic is mentioned here. Data is specific roles. This section contains the code of the program. Oh, nice, nice, nice. I think these are just the regular variables. The star just means that uh, it can have 0 or more characters. Is it? This section contains constant data that is read only. Constant data that is read only. Okay, nice. Dot data. This section contains read write data. Okay. BSS. This section contains read write data with an initial value of 0. Read write data with an initial value of 0. Mm, read write data with an initial value of 0. Okay. What is the difference between this and this? I think it's just 0, right? Let's take a result of the syntax of the Linker script. Firstly, entry boot declares that the boot function is the entry point of the program. Okay. Then the placement of each section is defined with this sections block. Okay, nice. Nice. That's the boot function is the entry point. Okay. Okay. There it places the dot text section and instance starting with dot text from all files start at that location. So you're doing this to and instance starting with dot txt dot from all files star at that location. And instance starting with dot text from all files star at that location. So directly places the dot text section and any section starting with okay, from all files. Okay, okay, nice. The dot symbol represents the current address. Okay, it automatically increments its data space such as with star bracket dot text. The statement means advance the current address by 128 KB. Okay. Okay, nice. The align 4 directive ensures that the current address is adjusted to a 4-byte boundary. Okay. Okay. Finally, PSS is equal to dot assigns the current address to the symbol BSS. In C language, you can refer to the defined symbol using extend char symbol name. Offer many convenient features, especially kernel level. You can find real world examples on GitHub. Okay. So this is minimal kernel, all these things, boot. Okay. So let's try to do that linker script at least. So let's try to touch kernel totally is it. Okay, and then do vim. Okay, let's copy this So entry boot sections. So entry boot is basically you're telling the linker that the boot is the function to start with. Sections is equal to, and that the current address, the base address is set to x 802. How many zeros those are? How many ever zeros those are? And then dot text is basically you're putting in the text. Um, and you're defining these sections uh, as the order these subsections are written in. So dot text dot row data. Row data. What does row data mean? Is it read only data? Yeah, it's read only data, and data is just mm, data, read and write data. Basically, you're putting in read and write data, and all of the basically this line which says that star dot text dot this thing, put everything, put every thing that starts with text into here, into this text section, and then you put in the same thing for row data, and then the same thing for data, and then the same thing for BS is basically you're aligning for which is the 4 bytes for where is it 4 bytes. It's just the current address is adjusted to a 4-byte boundary. Okay, current address is adjusted to a 4-byte boundary, and then 128 is equal to this 128 KB. You're setting the address to 128 KB, and then you're doing stack top is the current address. So I think the stack top, which means that this will start in the first program stack. Okay, cool. I think that's cool. Save it and exit. Let's do minimal kernel. We are now ready to start writing the kernel. Let's start by creating a minimal one. Create a C language source code named kernel.c. I think if you just do kernel, let's see, it will create. Okay. So you're doing type def unsigned char uint 8 integer unsigned 32. So you're type defining it to char for integer 8-bit integer char, and you're calling 32-bit integer as int, and you're calling the 32-bit integer as also size t. Okay, extend char bss bssn stack top. So you're defining these variables called char of type char, which is basically integer, and you're calling them bss array bss array stack top array. So you're defining an array whose type is char. Char is just an 8-bit integer. You're defining three uh, arrays called bss and stack top. Okay, and then you're defining creating a memset function. That's exciting, dude. Crazy. I've only used memset in C, just like by just importing the appropriate libraries. So here we are defining memset. That's crazy. So void pointer memset void pointer buff char c size tn. So it takes the buffer and it takes the char and it takes the size tn, and then it does what it does is basically buff. You're assigning the buffer to the pointer p. Okay, you're basically pointing to the buffer, and you're typecasting it before pointing to the buffer. Okay, okay. And then while n minus minus, you're assigning the pointer p next address to c, and you keep on doing that until n is equal to 0, and then return buff. You're returning the buff. Interesting. And you're doing void kernel main, void memset. You're using this, calling on the bss, which is just read write data with the initial value 0. Cool. Bss end, and then you're doing 0, and then second character is c. Basically you're putting into 0 as c. So okay, nice, got it. So you're basically initializing every address of this bss, every memory address to 0, and then the size you're defining it as size t bss end minus size t bss. Oh, nice. And then you're doing an infinite loop. Okay, why are you doing an infinite loop? But okay. And then you're doing attribute section dot text dot boot, attribute naked. So you're setting the dot text dot boot section, and then attribute naked, and then you're calling this function boot. I mean, there is the explanation here, but okay, I'm just trying to figure out it myself. And then you're doing assembly volatile my mv, so you're moving this pointer to percentage, which means you're moving this to r, and jkernel main this thing stack top. Okay, I'm not sure about this function, but that's cool. So I think let's just type this, whatever this thing is. Let's just type this ourselves. Okay. Okay. So type def, type def, type def, type def. Hold on. Okay. Type def unsigned char u int is it 8-bit t. Okay. Similarly, unsigned int u int 32 underscore t. How do you change this? Is it I? How do you change this character though? Okay, no. How do I? I want to just delete till the end of the word, which means I have to do delete till end of word vim. I just forgot this, man. Oh, D uppercase. Oh, DW. Right. Capital D is a synonym for D. Okay. So it's just basically this. Alright, cool. What did I do? It did not change it till the end of the line though. If I do this, okay, cool. Um, insert type def. Okay. Then hold on. I'm sorry, I'm so bad at Vim. Yo. What happened? Type def uint 32 underscore d as size d. Okay. 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 Engineering extend. Let's just do G. Sorry. Okay. Let's do J. J. Insert. Okay. Let's do extend. Char. You're defining BSS. An array. You're defining this BSS dot underscore end. Then that double underscore. Sorry. Double underscore. And this thing stack top this thing and then void main void. Sorry, void. I'm so used to void main, bro. So you're defining this function which returns a void pointer, which takes in a void pointer, and char c size t n. Okay. Uint. Okay. Uint 8 scroll t. Oh, you're type defining the char to uint, right? Okay. Okay. Cool. Because you are dealing with the bytes, so you're defining. I'm sorry, I read that wrong when I read it. Basically, you type defining char to uint38, and you're type defining int to uint32, and you're type defining uint to size t again. Okay. Cool. And then you're doing b. What you're doing is uint pointer is setting this thing 32t. Basically you are basically type defining it, typecasting it rather. Buff. A type You're typecasting buff to UN32, and then letting the pointer p2 point to the buffer, and then while loop, while in minus minus. Let's just do this. Second. Alright, I'm back. 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 Okay. Yep. So we're doing this, and then hold on. So, um, yep. So this we're doing. Okay. So, okay. Insert. Okay. Damn it. So you're incrementing the pointer p. You're assigning it to c. Basically, you're assigning c to the um, p. Basically, you're dereferencing it and you're putting it to 0 basically in here. Nice. Nice. That's a pretty simple function though. Damn. I thought it was a complex function until I read this. Because we use memset all the time. Nice. Okay, nice. Doing this in Vim is so techy though. Forgot my indentation. That's cool. After that, void kernel main. Um, Hold on. Um, Kernel main. So let's do that, right? Void kernel main void second void um so we're doing memset. We're calling memset on on the BSS, right? On the BSS, which is the read and write. Okay. 0, and you're putting in the size as this thing BSS and minus BSS start. Pretty cool. Wow, man. Okay. And then you're closing it, and then return. You're doing a for loop, which runs forever, which is also interesting. Alright. Hmm. One second, hold on, hold on. Alright, 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 alright. Let's go, let's go, let's go, let's go, let's go, let's go. Also, shift it here. And then you're doing attribute. I don't know what that means. But okay. What does attribute mean? I do not know, but attribute section text.boot. Okay. Section. Okay. Text dot boot. Oh, okay, because we have defined it in kernel that this is dot basically sections. Yeah, I'm not too sure about this line. That's for sure. Okay, but cool. How do you go to the start of the line? Bro, I'm trying to figure out how to go to the start of the line. I forgot. Is it 0 0 is the start of the file? How do you go to the start of the line? No, I don't know. Go to start if 0 to move go to start of the line. No, beginning. Zero is to the start of the file, right? Okay, cool. So I'll just delete this thing. So I'm just gonna copy this thing, paste it. What is this? Naked. And there's a naked function here, which I'm not too sure. What does that mean? Let's type it. Void naked void. You know what? It's actually hard to type it. Void. ASM. Sorry. Assembly. And then volatile this thing. You're defining volatile as you're doing the mv operation, mv to sp, that's the destination I believe, and percentage this thing stack top. Then you're doing this backslash n dude, I need a keyboard, bro, and I need two hands. It's so hard. G kernel main. I actually do not know what this means, but let's see. What does this mean? So the execute kernel starts from the boot function, which is specified as the entry point in the linker script. In this function, the stack pointer sp is set to the end address of the stack area defined in the linker script. In this function, the stack pointer sp is set to the end address of the stack area. Okay. So we're defining the boot function, and in this function, the stack pointer sp is set to the end address of the stack area defined in the linker script. Okay, just end address of the stack area defined in the linker script. Then it jumps to the kernel main function. It's important to note that the stack grows towards 0, meaning it is decremented as it is used. Therefore, the end address, not the start address of the stack area, must be set. Okay. Nice. We set to the end address of stack defined in the link script. As this. Okay. Okay, cool. Nice. 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 Just so that I won't mess this up, I'm just gonna copy this and paste it. How do I select this thing, bro? How do I select multiple lines? I just forgot. There's some command. How do I select this line? This is a visual mode. Is it? Okay, 1 second. So this visual mode, I think. Okay, yeah. So selecting this and just doing that. Oh, pretty nice. Cool. That's pretty cool. J, J, J. K. Sorry, J. And then H. H. Insert. And then command V. Sorry. U. Sorry. U. I'm just gonna copy this and paste it here. I'm gonna do U again. I have to delete this too. Visual mode. And then delete. And then copy that. And then copy this and then cool. And then you're doing that. Cool. Okay, that's cool. Now let's just do this. And again, this is what we wrote. So the execute kernel starts from the boot function, which is specified as the entry point in the linker script, and this function the stack point is set to the end address of the stack area defined in the linker script, which is stack area. This function sp is set to the end address of stack area defined in the linker script. Okay, nice. Then it jumps to kernel main function. It's important to note. So it jumps to kernel main after doing this. Basically, set the stack pointer to the start address, which means because stack grows downward. It's important address to towards 0 basically, meaning it's decremented as it used. Therefore, the end address, not the start address of the stack, must be set, because and that's why you're doing stack top and not the start address. Cool. The boot function attributes has no special attributes. The attribute naked attribute instructs the compiler not to generate unnecessary code before and after the function body, such as a return instruction. Oh, okay. This ensures that the inline assembly code is the exact function body. Nice. Attributes controls the placement of the function in the linked script. Nice. Which controls the placements of the function in the linked script. So it places in the text.boot here, which is here. Nice. Nice. Yeah. Since OpenSpace simply jumps to without knowing the entry point, the boot function needs to be placed at this. Nice. Nice. So extend char to get linker script symbols. Extend char to get the linker script symbols. Nice. Nice. Okay. At the beginning of the id symbol defined in the linker script is declared using extend char. Here we are only interested in obtaining the address with the symbols, so using char type is not that important. Okay. Okay, yeah. You can also declare it as extend char basis, but basis alone means the value at the 0th byte of the basis section instead of the start address of the basis section. Therefore, it's recommended to add this thing to ensure that basis returns an address and prevent any careless mistakes. Oh, okay. You can just define it like this, but the value at 0 byte of the basis section instead of the start address of the .basis section. Nice, because arrays are basically pointers in C. And .basis section is lesson. The kernel may fix the .basis section is first initialized to 0 using the memset function. Although some bootloaders may recognize and 0 clear the .basis section. But we initialize manually just in case. Finally, the function enters an infinite loop and the kernel terminates. It enters an infinite loop and the kernel terminates. Where does it terminate though? Because we are entering into an infinite loop, so okay. So like where does it end, like where does it, how does it terminate though? So let's see this thing. I think this will be just want to check later for this thing. Just wanna notes.md is good. Notes.md, which is this, and okay. Add a kernel build command and a new QEMU option to run.sh. Add a kernel build command and a new QEMU option to run.sh. Okay. So build in the kernel using this path to clang and compile the files. Ubuntu users use cc is equal to clang. C flags is equal to whatever this is. So using clang instead of gcc. Interesting. Build the kernel cc c flags wl tkernel.ld. Okay, minus wl map kernel.map minus o kernel.elf, and slash kernel.c. Kernel is basically okay. Okay. I'm not. I'm half sure what that means, but um, it's the LD that we're looking. Yep. Insert Control A. V. Sorry, just V visual mode and then control everything. Delete this thing and then paste it. What do we do? Oh no. You have to paste this. Yeah, okay. And then pretty much that. And then you can check the file by the home version Clang on macOS with the following. Let's see that. What? Command not found. Oh, I'm sorry. Just remove this dollar symbol. Where is this? Let's just open a normal terminal. It just gives me that, but okay. So we've done that, and this is the options that the C flag variable has. CUC1102 enable optimize to generate efficient machine code, generate the maximum amount of debugging information, enable major warnings, W extra additional warnings, compile for 32-bit RSCV. Okay, nice. Do not use standard library or the host environment, your development environment. Okay. Notice SVLab, do not link the standard library, WL tkernel.le, specify the linker script. Nice. Put a map file linker allocation result. Means passing option linker instead of the C compiler. Nice. Clang command does C compilation and executes the linker internally. Your kernel, if fast kernel debugging when you run and doesn't if there are no indications that the kernel is running correctly, but don't worry, this is quite common in low level development. That's where debugging features come in. To get more information, CPU registers, open the QEMU monitor and execute the info register command. Okay. So let's run it. Let's run the let's run the script. Is it okay? Okay, we ran the script. We are in here, but there's no indication that the kernel is running. That's true. So open the QEMU monitor, which is Control A. C. Okay, we are here, and then type info registers command. Info registers command. is this? CPU is equal to this thing number 0, V is equal to 0, PC. What are all this? What are all this? Oh, so the exact values may differ depending on the versions of Clang and QEMU. PC is the address of the instruction to be executed. Program counter 0. Damn. But there's something here. The address of the instruction being executed. Let's use the disassembler LLVM object dump port. So that means the program is not running, which means I have done some mistake. So I think let's just modify our thing correctly that it runs. Oh damn, shit, I just created a new file. Okay, cool. So okay, and then let's run it again, and then do Control A C. Let's go into QEMU monitor, and then do info registers. Still not, PC is still not updated to other values. Let's see what the next part is. LLVM object dump minus t kernel.elf. That is the instruction being executed. Let's use a disassembler to narrow down the specific line of code. Okay. LLVM object dump minus t kernel.elf unknown command. This thing. What do you mean, bruh? In bash. Okay. Not in QEMU. Okay, let's do that. And it says this. Yo, why does it say that? Let me open. I think it's due to the Clang. Basically, it's not. The path is wrong. So let me just check it. Like, why does it say no command found? Didn't we install LVM? Yeah, we installed this. Let me just do that again. Sorry.